Thank you for that introduction. And can everyone hear me online? Okay. Yeah, so today I'll be talking about a climatology of snowfall events over the United States Central Great Plains. And so in the background of this photo, I have a picture of some cars stuck in traffic, just showing some of the societal impacts that heavy snowfall events can cause. And getting into this a little bit more, winter weather events have large societal impacts and they are challenging to predict. A good example of this is the 2011 Groundhog Day blizzard, which caused 36 deaths and billions of dollars in damage across much of the central United States. And this map on the right shows the snow depth estimated over that region. And these events are generally pretty difficult to predict more than a week or so in advance, just due to the challenging and chaotic nature of the atmosphere. But there's been some work on S2S prediction to try to enhance the time window at which we can predict things. So getting into that a little bit more, if we want to look at S2S prediction of winter weather, we first need a good snowfall data source to compare the effects of different S2S drivers to. And furthermore, not only is the S2S effects on snowfall important, also snowfall can have effects on other types of weather phenomena on the subseasonal or seasonal timescale. One example of that is in hydrology. So it's been found that if there is a snowy winter in an area, there's more likely to be a rainy spring and summer because there's more moisture available for evaporation and later precipitation. And so better prediction of snowfall can improve hydrological prediction. Furthermore, improved snow cover prediction could lead to improved temperature prediction. And so snow cover has a high albedo, and so it tends to keep things cool, and so it can affect temperatures, especially near the surface and the boundary layer. And furthermore, temperatures above freezing, a lot of that energy will go into melting snow instead of raising the just a sensible temperature. And so that means that being able to predict snow is very important for temperature forecasts, and even improving that at the 2 to 3 week time scale is helpful. And so some research goals here. First is, what are the spatial characteristics of snowfall events in the Central Great Plains of the United States? Supplemental to that is, how do these characteristics compare between surface station and satellite measurements? And how do these characteristics change over time? And as far as hypotheses go, one is that snowfall events will typically cover around half of the coverage region, just based on the synoptic scale of these events. And secondly, that satellite will show greater areas of snowfall because it cannot detect the lowest area near the ground, and so it won't miss some of the snow melt. And also that over time, snowfall events will decrease in frequency but increase in intensity due to generally warmer and wetter atmospheric conditions. So getting into some data sources here, the primary source of snowfall data is surface station measurements from the Global Historical Climatology Network, or GHCN. This contains a record of snowfall events from the late 1800s to the present. And these are snowfall events that are measured daily by an observer. And the map on the right just shows where there are stations with snowfall data across the US. And I'll be focusing on the blue box region and the Central Great Plains for a couple of reasons. Primarily that there's fairly frequent snowfall there, and also there are limited effects from oceans and topography, so it's an easy area to start with for some analysis. And I'm going with the 1979 to 2022 time period because that is the start of reliable teleconnection and reanalysis data. And to talk about how I'll analyze these events, I think it's easiest to just walk everyone through a case study. So I'll be looking at one in December 16th to 17th of 2010, which was a fairly moderate and typical snowfall event across the region. So it's a good comparison for what a typical one might be like. And there tends to be, as you can see over parts of Minnesota and Iowa, a band of about 10 to 12 millimeters of liquid equivalent precipitation, which equates to about 100 to 120 millimeters of snowfall accumulation, which is about what you would expect with typical 10 to 1 snow ratios. And if we want to figure out what's going on in between these points, from this slide, we can use a technique known as kriging, which is just a good geostatistical interpolation technique. And it uses a function known as a variogram, which is shown on the right. And this shows the semi-variance, or half the variance between stations, as a function of their distance. And so generally stations that are close together will have less variance because they'll be more affected by the same physical phenomena that are producing the precipitation. And then if stations are farther apart, they'll be possibly having different effects or be in a different area of an extratropical cyclone, so you'll get more different values. So that's why you'll see the semivariance increase with distance. And then there is a range or a decorrelation distance beyond which there's basically no correlation between points, and you're just at a larger scale than the storm system. And then the SIL is the maximum amount of semivariance. So how much variation is there if they're just completely random far apart points? And the nugget here shows the amount of variability that's smaller than the station scale. So this should be fairly small for synoptically driven events, because if stations are 50 kilometers apart, they should have similar values. And so from this, we can sort of invert it and get a function of covariance, which would start higher up and go down as closer stations are more closely related that way. And so at any given point, closer stations will be weighted more highly based on the covariance function derived from the variogram. And so when we run this kriging procedure, we will see that the closer stations are the better the weighting is. And there's also, this accounts for uncertainty as well, which is useful to know how accurate your estimates might be. So yeah, showing this, we then have the kriging uncertainty estimation, or the kriging values across, and you see the same snow band across Minnesota and Iowa that you saw with the surface station data. So that's good to see that it's actually interpolating things well. And on the right is a figure showing the standard deviation error in these estimates. And these black areas are where the stations are, and there's going to be very little uncertainty there because you're close to a station. And then the pinker areas are farther from stations, so there's going to be more uncertainty. And if you compare the uncertainty values to the measured values, it's about 10 to 20 millimeters out of about 160. So that kind of just gives you a sense of the errors, maybe about 10% in heavier snowfall areas. But this data is not perfect, so there's been some quality control on it. So the GHCN network already quality control stations for very high or very low values, or many repeated values, and there are some other procedures to remove clearly unphysical values. But there's not as much quality control in the spatial regime. So sometimes stations will have a reported zero value when there's not actually a zero value, or they'll report data on a different day than other stratum stations. Just a lot of manual, like co-op sites, for example, someone might report it late or something of that nature. And so if you look at our case from before, that was a 2-day event, you see this one station marked by this arrow in Minnesota, where there's no values on the 16th when surrounding areas have heavy snowfall. And on the 17th, there is that heavy snowfall reported when it's lighter values in surrounding stations. So that station was just off by a day in their reporting. And so to account for some things like that, we can do a technique called leave one out cross validation. And this is where we redo the kriging procedure with each station removed. So you do it about, say, 100 times if there are 100 stations. And for each station, we see how much the values change when that gets redone. So if a station has a zero value and it's more than 3.5 standard deviations below what the kriging estimate is when the station is removed, we suspect that it's a false zero value and discount that station. And so this is a fairly tight criterion because we don't want to unnecessarily remove values. And there is one challenge, though, which we still need to resolve, which is that sometimes there can be a sharp gradient. And so there might be a place that really did get zero snow, and there would be would be 3.5 standard deviations below the estimate if that station was removed, but it could be legitimate. So that's something that'll be worked on in the future. But so when this quality control is taken care of, what we see is that certain points can get removed. So here there was one in the Minneapolis-St. Paul area. And since this is a 2-day event, the one I pointed out earlier is okay because the 2 days are combined, but this point still had zero value. And so the variogram will be recalculated. So this is the variogram with outliers involved and then without it. it shifts a little bit. Usually there's not a dramatic shift from removing these outliers, but still provides some better data. And if we look at the kriging procedures, comparing outliers versus no outliers, they're fairly similar, but there are slightly more in the no outliers one. You can see the color bars, the max is 200 millimeters for outliers being removed compared to 160 for outliers being present. And so this is fairly typical. What we'll see is that there are some modest changes to the snowfall patterns, but it's typically nothing dramatic. And so now that we have this basic idea of the spatial field of a snowfall event, we can also figure out some more information about it. So first of all, for anything to count as an event, it has to have at least 30 millimeters of snowfall to remove any light events. And some can last multiple days. And so this might be kind of hard to see, but there's two light blue contours which show areas of at least 10 millimeters of snowfall or more. And one is on December 16th and one is December 17th, and they overlap. And so that's basically how we determine a multi-day event, is if there's overlap in the 10 millimeter snowfall accumulation areas, then it's probably an event that's propagating across the country, not two separate events. And with all this work, we found that there are approximately 1,500 events in the entire 44-year data set. And so for a little bit more about this, for every event, we compute some statistical characteristics of them. And these can include the area. So this is a 10 millimeter outline of the December 16th to 17th snowfall event. And then there's the volume. So that's basically the area times the average value of snowfall across the region. And that's important for hydrological purposes because that's basically how much water is being deposited over the region. And there's the maximum value and the mean value. And so here are some snowfall statistics for these events. So the area is the area within the 10 millimeter contour. And you can see that there tend to be a lot of events that are relatively small in area. And that was a little bit unexpected to me because I was kind of imagining that these events would be larger. But I think a lot of events have some rain in certain areas or might just not have as much snowfall accumulation as you might expect. And maximum values here, you can again see that there are most events have relatively light accumulations, which is typical of precipitation. Most events are lighter. And the reason there's nothing less than 30 here is again because that was the minimum threshold set to ignore any really light events that would not be very impactful. And we also have a few other variables plotted. So there is the snowfall average values. So that's just the average snowfall accumulation within the 10 millimeter contour. And so you can see that there's a modal peak in the 20 to 40 millimeter range because it can't be less than 10, but still most values are going to be smaller. And another statistic we have is the snowfall volume on the right, which is the average snowfall accumulation times the area. And since both the average accumulation and the area tend to be most concentrated on the lower values, you see that even more extreme when you look at the volume with only a few events being in the right half of the histogram. And we also wanted to look at how good our variograms are, so we computed some statistics there. So first is the nugget relative to the sill. So we wanted this to be a relative measure because a event with very heavy snowfall would just naturally tend to have a higher nugget just due to there being larger values. But if we account for that, we find that usually the nugget is quite small, which is good because that means that stations are fairly accurately able to capture the spatial variability of a synoptic scale snowfall event. And on the right is the range, which is again showing how far you are before the 2 points are no longer correlated. And this tends to be in the 200 to 500 kilometer range, which again gives you a sense of the spatial scale of these events typically. And I also wanted to look at some of these trends over time. And I was hoping to get all 44 years in here in time for the seminar, but I only got to about 23, but this should still have some good data. So if you look at the mean area of events and the mean accumulation, there are slight increases, but the trend is fairly weak, and I'm not sure if it will be statistically significant. I'll look into that in the future. In terms of number of events per year, there's a slight decrease here that may or may not be statistically significant. And then for the mean maximum accumulation, we see that the values tend to be about 130 to 140 millimeters across the entire time span. And for the mean volume, it's increasing slightly as well. So it seems like there may be somewhat of an increase in the area and thus the volume, but it's hard to know if that's a significant trend or not. And so future work will hopefully delve into that some more. But now we've talked a lot about the surface station data, and I want to compare it to satellite data because that has broad spatial coverage, and you don't just have to interpolate, you can actually see what the satellite is estimated. And so there's something called IMERG, which is the Integrated Multi-Satellite Retrievals for GPM, which is a precipitation product based on satellites, and it runs from the early 2000s to the present. And it has precipitation data every 30 minutes using a combination of both radar and diameters. And you can see this collection of satellites on the right. With a different space agencies such as NASA, the Japanese Space Agency, France, India, and the EU have all launched different satellites to participate in this. So that improves the spatial coverage of it because these are all low Earth orbiting satellites, so they can't cover as big of an area as like a geostationary satellite. And this is an image showing the core observatory satellite of and how it scans. So there's a dual frequency radar, which is in the KU and KA band. And so this dual frequency radar can help better determine precipitation through looking at like differential attenuation between the different frequencies, for example. And these are both higher frequency than your typical S-band radars used by the Weather Service or your X-band radars even, but you need something smaller to fit on a satellite, so that's why they do this. And this is there's only one satellite radar, but then there are several passive microwave radiometers, and these measure emission in the microwave bands that correspond to rain and snow. And so this way you can get broader coverage and estimates, even if it's not quite as accurate as the satellite radar. And so for this, the reason we want to do this comparison between satellite and ground observations and where the boundary layer is relevant is that satellite radars cannot collect data in the lowest kilometer or so due to ground clutter from the radar signals. And so there can still be substantial melting or refreezing of hydrometeors at this level. And so what you're measuring at 1 or 2 kilometers might not be the ground truth. So it's always challenging to figure out how to account for that. And so a comparison of satellite and surface station measurements can then be used to determine the weaknesses of satellite snowfall estimates in the boundary layer. And the goal then is to create a combined satellite and surface station database to get the reliability of station data with the broad spatial coverage of satellite data. And I've started just very initial comparisons of these two measurements. And so this is the same case as before, where on the left is the snow estimate from IMERG using their precipitation estimates and weighting by less than 15% probability of liquid precipitation, which is often what people use to determine if it's rain or snow. And you can see that if you account for the fact that IMERG measures liquid equivalent and surface stations measure actual depth on the ground, if you account for that 10-to-1 ratio, it looks about right, but there is a much broader area of snowfall in the IMERG data set. So that is most likely, I would suspect, due to some sort of melting in the boundary layer that's getting missed because there was some precip measured in these areas in surface stations that was not reported as snow. So definitely be looking into this in more detail and doing similar statistical calculations of that, what I did with the station data. And lastly, I want to get back into teleconnections because the goal of this whole data set is to enhance prediction of snowfall on the subseasonal to seasonal timescale. And so teleconnections are one way to do that. These are relationships in atmospheric variables or patterns in one area with those in another area. Teleconnections are often the effects driven by climate modes or patterns of climate variability. Some examples of these include the Madden-Julian Oscillation, or MJO, which is an area of enhanced equatorial convective activity that gradually propagates eastward along the equator. There's the North Atlantic Oscillation, which is a pressure variation between Iceland and the Azores. There's the El Nino Southern Oscillation, which is a change in sea surface temperature and pressure over the central and eastern equatorial Pacific. And there's the Pacific North America pattern, which is a pressure variation between the central and North Pacific, Western Canada, and southeastern US. And so some of these have been found to have effects on snowfall across the US. For example, the La Nina has been associated with an increase in snowfall over the Great Plains. There has been a negative correlation between the Pacific North America pattern and snowfall in the Great Lakes region. There's a negative correlation between the Arctic Oscillation and snowfall in the central US. And the MJO associated convection in the maritime continent is associated with increased snowfall in the central Great Plains, which was what some of my master's research was on. And this figure kind of shows the snow accumulation with the ratio relative to climatology, with the blue being the uncertainty bands. And you can see that in phases 4 and 5 of the MJO, which corresponds to that convection over the maritime continent or the Indonesia area, there is enhanced snowfall compared to otherwise. But there hasn't been as much study of these teleconnections in combination over a long time scale, because, for example, you can have a La Nina and a negative Arctic oscillation and a positive Pacific North America pattern, and how all those relate to each other has not really been studied that much. And so my research goals for the next stage of my work is to basically ask the question, how do various global climate modes, such as the MJO, ENSO, NAO, and PNA, affect the frequency of winter weather events over the United States, and to what degree can they be predicted on the S2S timescale? And then my hypothesis is that changes in winter weather event frequency are caused by changes in the flow pattern influenced by different climate modes and by their effects on temperature and dynamic processes. And these answers will come hopefully the next year or two, so stay tuned. And as far as some basic conclusions go, kriging can be used to compute the geostatistical characteristics of snowstorms. The bulk of snowfall events tend to be smaller in magnitude, both in terms of like their area, maximum value, average value, and so on. And satellite data tends to show more expansive areas with snowfall as compared to station data. So melting in the boundary layer is likely an important issue there that satellites have trouble detecting. And there tend to be fairly weak trends in snowfall characteristics overall, but they may be present in some cases. So I hinted at this future work earlier, but just to clarify it a little bit more. First, I want to finish collecting data on snowfall events and compute this statistical significance of these trends. Then to continue the satellite analysis of snowfall events and compute the same characteristics like area, maximum value, mean value, and so on based on satellite. And then also determine monthly variation in snowfall events, so how things compare in November versus February or March. And then the next big project will be to determine how climate modes such as ENSO or the MJO affect snowstorm characteristics using this database of both station and satellite data. And lastly, for my acknowledgements, I'd like to thank my advisor, Dr. Pierre Kirstetter. I'd also like to thank the NASA scientists, Dr. Lisa Milani and Dr. Sarah Kasimi, who helped provide information about satellites and snowfall. And I'd like to acknowledge my PhD committee of Dr. Jeff Becerra, Jason Furtado, Kathy Pichon, and Shannon Doolin, in addition to Pierre, and my family and friends, some of whom are in the audience today. I'd like to acknowledge my pet fish and snails, and here is a photo of my fish tank. And my friends convinced me to do a weekly snail census, and here is the snail population. So with that, I'll bring it back to the conclusions, and I'll take any questions. Thank you. Yes, have it. So we started with 3 standard deviations and thought that sometimes removed values that looked like they should still be included. But 3.5 didn't seem to do that so much, so it was definitely kind of an empirical. This seems to be about a good threshold. Yes. So I think what's happening there is that it's sort of reached the carrying capacity of the fish tank, and so it's kind of now balanced out. Yeah, so I chose that mostly just because that seems to be about where there can start to be some impacts in certain scenarios. Like if it's just a quarter inch or something, then it doesn't seem to ever really affect transportation unless there's like ice or something involved. So it would be interesting to like look at slightly different thresholds, but just seemed based on my experience with observing winter weather events in general, it seemed like about where things start to have impacts. No question? Um, so it has a good sense of like the uncertainty and the estimates, and so that's a benefit of it. And it also like if you look at say inverse distance weighting, that always seems to create like a very overly smoothed out results, and so this seems to better preserve the spatial features than a lot of other methods that could be used. And there are things that we could do to be more complicated, like look at anisotropy or whatnot, but this seemed like the most straightforward way to do a preliminary analysis.